Hi all. So in this video we are going to discuss actually the second module of the linear control system of the KTU syllabus, that is the time response analysis. So before going to the analysis, we must know what is the time response and what are the standard signals. Okay. So the time response of a system is the output of the closed loop system as a function of time. Okay, and it is denoted as C of t. Okay, the closed loop transfer function C of s by R of s. This is the transfer function normally we are using. C of s by R of s can be expressed as G of s by 1 plus G of s into H of s, and we are using a term M of s for denoting the transfer function. Okay, so the output or response in S domain, that is C of s. Okay, C of s is given by the product of this transfer function M of s and R of s. Okay, input R of s. So C of s will be equal to R of s into M of s. Then on taking inverse Laplace transform of this product, the time domain response C of t can be obtained. So C of t is equal to Laplace inverse of this C of s, and which again is equal to Laplace inverse of R of s into M of s, where M of s is the transformation M of s by 1 plus G of s into H of s. Okay, so C of t is the time response of a system. And normally the time response of a control system consists of two parts that all of you must know about it. That is, there are two parts: the transient part and the steady state response. The transient response and steady state response. Normally the transient response is the response of a system when the input changes from one state to another. Okay, that is the transition period. And the steady state response is a response as time t approaches infinity. Okay, that is after transition period. Normally in some cases the amplitude may be same. Okay, for different when the time increases, the amplitude is keep on constant. Okay, so we can say that the saturation occurs. So the steady state response is a response as time t approaches, that is at time t approaches infinity. Okay, so next we are moving to the test signals. What are the standard test signals we are using in control systems? Okay, actually the knowledge of input signal is required to predict the response of a system. Okay, so based on the input we are giving to a system, the output changes. Okay, so in most of the systems the input signals are not known. Okay, are not known ahead of time, and also it is difficult to express the input signals mathematically by simple equations. Okay, so the characteristic of actual input signals are a sudden shock, a sudden change, a constant velocity, and a constant acceleration. So hence test signals which resembles these characteristics are used as input signals to predict the performance of a system. So actually, to predict the performance of a system, we have to use some test signals which resembles the characteristics such as sudden shock, sudden change, constant velocity, and constant acceleration. Okay, so the normally used standard test signals are step signal, and another form is unit step signal, then ramp signal and unit ramp signal, parabolic signal and unit parabolic signal, and impulse signal and sinusoidal signal. Okay, so these are the main test signals we are using. So in that, the first one is the step signal. Okay, so the step signal is a signal whose value changes from 0 to a, that is 0 to a at time t is equal to 0. So this is the time t is equal to 0. So at that time the value changes from 0 to a and remains constant at a for t greater than 0. So the step signal resembles an actual steady input to a system. Okay, so this resembles an actual steady input to a system. A special case of step signal is unit step. Okay, unit step where this a becomes 1. Okay, if the amplitude is 1, we can call it as a unit step signal. Okay, so the mathematical representation of the step signal is R of t is equal to 1 for t greater than or equal to 0, This is the representation of unit step signal. Okay, and it is 0 for t less than 0. Okay, so the next one is ramp signal. So the ramp signal is a signal whose value increases linearly with time. So here you can see the value is increases linearly. Okay, uh, the ramp signal resembles a constant velocity input to the system. Okay, it resembles a constant velocity input to the system. So the special case of ramp signal is unit ramp signal, in which the value of a is unity. So here the amplitude is denoted as a, 2a, 3a, like that. If the a is unity, that is 1, 2, 3, 4, like that, then it is called a unit ramp signal. So normally the ramp signal is represented as r of t is equal to at for t greater than or equal to 0, and it is 0 for t less than 0. And next test signal is parabolic signal. So in parabolic signal, the instantaneous value varies as square of the time from an initial value of 0 at t is equal to 0. So from this time onwards, the value, the output value varies as a square of the time. So it resembles a parabola. Okay, so a parabolic signal resembles a constant acceleration input to the system. So this is a parabolic signal, so it represents a constant acceleration to the system. So a special case of this parabolic signal is that when this a becomes 0, when this a becomes 1. Okay, so normally the mathematical representation of parabolic signal r of t is as at square by 2 for t greater than or equal to 0, and 0 for t less than 0. Okay, for t less than 0 it will be 0. So representation is at square by 2. In the previous RAM it was at, so here it is at square by 2. And the next one is impulse signal. So a signal of very large magnitude, a very large magnitude which is available for a very short duration is called impulse signal, like a sudden shock. Okay, so ideal impulse signal is a signal with infinite magnitude. So this is an ideal signal with infinite magnitude and 0 duration, but with an angle of with an area of a. Okay, the area of the signal we are calculating as a. The unit impulse signal is a special case in which a is unity, that is, in which a becomes 1. So the impulse signal is denoted by delta of t. Okay, so delta of t is equal to infinity for t equal to 0, and t is 0 for t not equal to 0. Okay, so that's the case of an impulse signal. I hope all of you understand the standard test signals well. And here, for a unit step, if you are taking the Laplace transform, if you are finding the Laplace transform, that is r of s, that is capital R of s, it will be 1 by s. Okay, it will be equal to 1 by s for unit, and it will be equal to a by s for the step signal having a magnitude of a. Okay, magnitude of a. And in the case of a ramp signal, it is denoted as at, and the Laplace transform r of s is equal to, we know that it will be a by s square, that is Laplace transform of at. At is a by s square. Okay, and for a unit ramp it will be 1 by s square. And for parabolic, the representation is at square by 2, and the Laplace transform will be, that is r of s, it is equal to, r of s is equal to a by s cube. Okay, when it is unit parabolic, a becomes 1 and r of s equal to 1 by s cube. Okay, and for an impulse signal, the Laplace transform delta of t is 1. Okay, so I hope all of you understand the standard signals and its Laplace transform well. So thank you.